One of those things that we use Lineweaver-Burk plots or those double reciprocal plots for quite often is when we're looking at reversible enzyme inhibition. And so this is an important concept when we're considering pharmaceuticals because a lot of drugs are reversible enzyme inhibitors. And so these are inhibitors that bind non-covalently, hence reversible. So they're interacting in the active site through hydrogen bonding interactions or nonpolar interactions, those types of things. And really, there are a few different flavors of inhibitors, and we can think about these a few different ways. I approach this a little differently than your book does, but we kind of get to the same place. And a particular inhibitor is going to bind in one of the following places. It can be within the active site, where it's going to bind in the exact same place as the substrate in question. So it's going to occupy that substrate's binding site. It could be in an allosteric site, so somewhere else. Another possibility is it actually binds within the active site, but in a place not where the substrate we're looking at, but where the second substrate binds. And so we'll explore all of these things. Now, depending on how and where these inhibitors bind, they can change the Km or Vmax values, or both. And we call the altered value an apparent value because that's the way it appears in the presence of that inhibitor. So we'll say Km apparent or Vmax apparent. Now, the first one I want to talk about, and the one that is probably by far the most common, is what we would consider a competitive inhibitor. And this means that it's going to bind within the active site and actually prevents the substrate from binding. And so, conversely, if the substrate's already bound, the inhibitor can't bind. And so binding of those two, the enzyme, is mutually exclusive. Only one can bind at a time, and thus they are in competition with each other. And so a scheme for this, remember we started off drawing before our initial velocity scheme like this, where we have enzyme substrate complex forming from free enzyme and free substrate via this equilibrium, and then Kcat then governs the formation of free enzyme and product like this. And so for all these modes of inhibition, I want to identify where's the inhibitor acting. And we said that the inhibitor is in competition with the substrate, so it can only bind to the free enzyme here. The inhibitor cannot bind to the enzyme substrate complex, for example. So this is an equilibrium process to produce this enzyme inhibitor complex, and this is a dead end. Right? Nothing can happen to the enzyme with the inhibitor bound because it's blocking the site where the chemistry is supposed to take place. The only thing that can happen is it can unbind, the inhibitor can unbind, and the substrate could then subsequently bind. Notice there is this equilibrium here, and we're going to call this equilibrium, label it Ki. Ki is exactly the same thing as Kd was before. It's a true dissociation constant, and it tells us how well the enzyme inhibitor bind. And so a lower Ki indicates a tighter binding inhibitor. A low Ki value indicates that the equilibrium favors the formation of the enzyme inhibitor complex. And just to draw a little picture, just so we're clear about what's happening, the normal thing is that the substrate can bind within the active site, and it can go on and make product. But in this case, we're saying that this inhibitor is going to bind in the exact same spot, and it's going to prevent the reaction from occurring. So let's look at a Michaelis-Menten plot for competitive inhibition and also the equation. So let's plot initial velocity as a function of substrate concentration. And I'm going to first look at the regular reaction with no inhibitor. So we'll look at a plot that looks like this. So we'll label this one no inhibitor. And of course there's some Vmax value associated with that reaction, whatever it happens to be. So if we add an inhibitor now, a competitive inhibitor, remember that the inhibitor and the substrate are in competition, and so if we add a whole bunch of inhibitor, if we add a whole bunch of substrate, we can actually wash out the effect of the inhibitor. So there's inhibition is obvious at low substrate concentrations, but at high substrate concentrations, we actually don't see any inhibition. And that's the key concept for competitive inhibitor. So with an inhibitor, this curve is just kind of stretched out to the right. like this. It eventually reaches the same Vmax. So this is with inhibitor here. So we're looking at the same Vmax, and so half Vmax is going to be the same. All right, so this is the Km with no inhibitor. Draw that line over here. And then we drop this down. This is now the new thing we're going to call Km apparent. It's the apparent Km. So a competitive inhibitor increases the apparent Km versus the regular Km. Why is that? Well, first let's look at the fact that the effective enzyme concentration is unchanged. Because we can add more substrate to diminish the effective inhibitor, we have no change in Vmax versus Vmax apparent. But the requirement to increase the substrate concentration to make that happen appears to decrease the affinity that the enzyme and the substrate have for each other. Hence why Km apparent is greater than Km. Now, that doesn't mean that the enzyme and the substrate actually physically interact less tightly. It's just you have some population of the enzyme that is bound by that inhibitor, and so in order to swamp that out, we have to add more substrate to the reaction. So let's look at the Lineweaver-Burk plot for competitive inhibition, or the double reciprocal plot for this. And what I'm showing here is, again, a series of substrate concentrations, different velocities that are produced, and we're doing those at 3 different concentrations of inhibitor. And so the first one is 0 inhibitor, and that's going to look a lot like what we've seen before. So this is 1 over the initial velocity as a function of 1 over the substrate concentration. And the first thing we would see is should be a slightly more shallow curve. We'll just do 3 points, since that's all the data that this plot is showing. And I will sort of carry that back like this. And this is the one where the inhibitor concentration is 0, so uninhibited. The next one is where we have some inhibitor, and the line for that one, the slope will increase a little bit. So now I'm going to draw this kind of like this. And so this is the next one, which should look like this. This is the inhibitor equals 1 series. And if we add even more inhibitor, and again, I'm not specifying exactly what the concentration is, we're just saying it's increasing, it's going to look like this. So this is for inhibitor equals 2, whatever the units happen to be. And what we'll notice is the following pattern. There's an intersection point on the y-axis right here. Well, remember, in a Lineweaver-Burk plot, that's 1 over Vmax. And this is what we expect. We expect that there's going to be no change in Vmax for a competitive inhibitor. But we do see changes here. Right? This is negative 1 over Km, the normal Km. And then both of these are negative 1 over Km apparent. And of course, that Km apparent is going to change based on how much inhibitor is added. So now that we know that, I want to return back up here and look at this equation set that we have here. So here is the sort of modified version of the Michaelis-Menten equation. Notice it's got Vmax S and alpha Km plus S now in the denominator. Alpha is a term that's going to describe to us the effect of the inhibition. And so the apparent Km is that alpha value times whatever the normal Km is. And look what's within alpha. It's 1 plus, here's the key part, it's the concentration of inhibitor divided by the Ki value for that inhibitor. And so remember, Ki is an indicator of how tightly an enzyme and inhibitor bind. So if we have a very small Ki value here, and the denominator, that's going to make this term very large. It's going to make alpha large. It means we're going to have a big effect of the inhibitor. It's going to cause, right, the Km apparent to be a larger number. Likewise, if we increase the concentration of inhibitor, it's going to make alpha a large number and make Km apparent large. So the ways to have a larger Km apparent is if we have a lot of inhibitor or if we have a very tight binding inhibitor. And so for all of these types of inhibition things that we're going to look at, I highly recommend being able to tie all of this stuff together. Notice that in the Lineweaver-Burk plot, that things are intersecting here on the y-axis, that tells us that for competitive inhibition, Vmax is not going to change. If you remember that inhibitor and substrate are in competition for the enzyme, it's going to take more substrate to achieve half maximal velocity because we have to push out the effect of that inhibitor.